My name is Harshal Mehta and my ID number is 24CS053 and our topic is converting multi-level English to single English. It's all about taking a complex multi-layered data structure and flattening it into simple linear one. Understanding multi-level English. First, let's understand what a multi-level English is. Unlike a simple list that only moves forward using a next pointer, each node in a multi-linked list can also have a child pointer. Child pointer can lead to completely different lists, creating multi-levels of data, much like folders inside other folders on your computer. So, what is our problem statement? So, what's our goal? We want to flatten this hierarchy. We aim to transform this complex structure into single long chain where only next pointers are used. And critically, the nodes must appear in level by level order. Original, target, and structure. To visualize this, the original structure has nodes pointing both sideways with next and downwards with child. Our target is clean, linear sequence where every node is concerned only by the next pointer, removing all the vertical complexity. Constant. An important rule for this conversion is that we must maintain breadth first order. This means we process all nodes at the top level first, then all nodes level down, and so on. We don't go deep into one branch before finishing the current level. Example transformation. Let's Let's start with the nodes 1, 2, 3, 4, and 5. Node 1 as a child, list 6 and 7. Node 3 as a child, list 8 and 9. After flattening correctly, the new list becomes 1, 2, 3, 4, 5, 6, 7, and 9. And so on. You can see how we can complete the entire first level before adding nodes from the second level. So the solution has basically two approach. The first is queue based approach. Now let's discuss how to achieve this. The first method uses a queue. The idea is simple. As we move horizontally through the list using next pointers, whenever we find a new node with a child, we add the child list to a queue. This acts like a waiting line, ensuring we process list in correct order. Steps in the queue method. Here are the clear steps. Whenever you find a child, enqueue it. Once you reach the end of level, dequeue the next list from the front and start processing it. This cycle repeats until the queue is empty perfectly, maintaining the level order. So we can we have initialized here, then we have run a loop to process all nodes. Then when last node is reached, we have done this. Then we have dequeued and linked to next level. Then if current node has a child, then we will do this. Then to advance the current nodes, we have done this.
My name is Krish Mandavra and my ID number is 24CS054. Now I explained the second approach. Its name is constant space method. While the queue method is very intuitive, it has a significant drawback. It requires often extra space for the queue, which might not be ideal in memory sensitive environments. This brings us to our second more optimization solution, the constant space method, also known as the tail pointer strategy. The fundamental goals here is to achieve the same level order flattening but without using any additional data structures. We want to do everything in place. How is it possible? We think that the inside in that we can use the list we are building as its own queue. We maintain two main pointers, a current pointer to traverse find child list and a tail pointer that always points to the very last node in the flattened list so far. Think of the tail as the back of the line. Whenever we discover a new group of nodes, a child list, we don't store it in a separate queue. Instead, we immediately direct the people at the back of the line to let this new group join the behind them. This method is elegant because it is modified. the list as it goes. Requires no extra memory, which gives it a space complexity of 1. That's just the pointer themselves. Uh, Now, step into tail pointer method. Let's walk through the tail pointer method step by step. Uh, Step 1. Find the tail. This is a continuous process. We don't just find the tail once, we constantly maintain a tail pointer. Initially, we might need to traverse to find the end of the first level to set our initial tail. After that, as we add new node, we advance the tail so it never loses its position at very end of our newly constructed list. Step 2. Traverse and append. We start a current pointer at the head of the list. We move this current pointer forward one node at a time for each node current visits. We check does it have a child. If it does not, we simply move current to the next node. If it does, this is where the magic happens. We take that child list and we connect it to the tail. Specially, we set a tail dot next to point to the head of this child list. The physically adds the entire child list to the main line. Step 3. Update the tail. After appending a new child list, our tail is no longer at the end. So this is a critical step. We must know traverse through the list. We just append the child list to find its very last node. We then update our tail pointer to that last node. The prepares us to append the list we find in the correct place. This child of traverse append and update the tail continues until the current pointer has gone through every node, ensuring all child have been woven in the main list in correct level order. Okay, so now solution comparison best practices. So with two method on the table, how do we choose? Let's do a direct comparison. Queue-based approach. Big advantage is simply the logic is very straightforward and easy to debug. The clear separation between traversing and processing via the queue makes the code reliable and less prone to the pointer errors. The drawback is memory. It requires often extra space for the queue in the worst case. If you have a lot of levels, this queue can become large. Tail pointer approach. The big advantage is efficiency. It uses only of one extra space, just a few pointers. This makes it is the superior choice for system where memory is scarce, like in abandoned device or operating system kernels. The drawback is complexity. Managing the tell pointer correctly, especially make sure it's updated accurately after every append operation requires carefully attention. The code can be slightly more tricky to get right. Therefore, use the queue-based method when you are prototyping when code clarity and maintain are you are your top priorities or when you know your data structure won't be extremely deep. Use the tail pointer method in production system where performance and memory footprints are critical and you are willing to invest a bit more effort into writing and testing robust pointer manipulation code. So thank you. And that concludes our deep dive into flattening multi-level linked list. We have explored two powerful techniques, one priority clarity with a queue and other priority memory efficiency with a Taylor pointer. Both achieve the same goal in off and time, so your choice ultimately depends on specific constraint of your project. Thank you for watching our video. Once again.